So what we got here is 8.1, day 2. Day 1, we talked about what a vector was and how you sometimes can name it and what would be considered a vector and not a vector. So vectors have magnitude, they have a direction. We talked about two different bearings. We got true bearing and we have, the other one was called, what was the other one called? True bearing was starting at north, always going clockwise. The other one was north-south. What's that? Quadrant bearing, thank you. So we have quadrant bearing, and that was first start south or north, and then go east or west a certain amount of degrees. So for our operations with vectors, you may want to actually kind of know what it means to have parallel, equivalent, or opposite vectors, okay? So on these, we got parallel vectors. Parallel vectors have the same or opposite direction, but not necessarily the same magnitude. So in this figure, the vectors of A, B, C, E, and F, so A, B, C, E, and F, so all of them but D, are all what we call parallel vectors. Some are going up to the right and some are going down to the left. They are still parallel because they have the same kind of direction, or differ by 180 even, right? So those would be considered parallel. Equivalent vectors, guys, have the same magnitude and direction. Now, I do believe I may have hinted at that the other day, because vectors don't necessarily have to be pointed in certain directions 100% sometimes too. Equivalent vectors. A is equal to C because they have the same magnitude and direction. In this case, to be equivalent, okay, we'll say equal magnitude, length, and direction. Otherwise, I guess we would consider them to be more parallel or opposite if they start falling in different directions. Opposite vectors. Or should I go back up there? We got some more information there. It says, notice that A does not equal B, since the absolute value of A does not equal the absolute value of B. Absolute value of A and B there really means magnitude. So I really should say the magnitude of A does not meet or equal the magnitude of B. Notice that they are going in the same direction for A and B, but B has a longer length, which means the magnitude is larger. Opposite vectors have the same magnitude but opposite direction. The vector opposite A is written as negative A. So E is the opposite of A, or negative A. So E, which is here, is the exact same length but opposite direction. So that is the opposite vector. What do you think happens when you put in opposite vectors together? It's like someone pulling a rope one way, you pull the rope back the other way. What would be the final displacement? What would you even see a change? You wouldn't, right? Be completely opposite of each other. If you witness this, you could see something happening. But someone walking in the room would not notice that that particular object was even affected or moved. So that's kind of interesting. And we'll talk about that here on the top, in that the resultant is the sum of two or more vectors into a single vector. Actually, I don't have that on this page. It must be the next one, called a zero vector. The zero vector is both zero vectors of, like the two, adding its opposite would result in a zero vector. No change. But the resultant, so when you hear the resultant, find the resultant, it basically wants you to add the vectors together. It's two or more vectors. So you can add 5 vectors together if you absolutely wanted to. Remember, a vector is a force with a direction. So at this point, every time you have a vector, you could be applying some kind of force or some kind of direction, force and direction, to an object. So if you think about your desk, you can push it to the left, you could push it then to the right, or north, south, east, west, in several different times. You add up all of those individual pieces, you could then instead create a pathway from where the position of the chair was originally straight to where it's now. Think of the Pythagorean theorem in a way, right? You could go all the way side 1 and then go all the way side 2. But you could just very well go from the first point all the way straight across to point B. Or all the way across, I guess, to point A, other side. So there are two different methods for finding the resultants. You got the triangle method, which they call tip to tail, which means the tip is where the arrow is, the tail is the non-arrowed side. And then the parallelogram method, that's the tail to tail. Both of these will work. So as you can see with the tip to tail method, you travel one vector and you have another vector. So when you add those two together, you're going to pick up the second vector and place it at the tip of the first one. So I'm going to travel A and then travel B. And the coolest thing about it is, just like I was saying, I can move the chair down to the right and then up to the right. Or someone else could have came in the room and just went straight across. And that green vector, A plus B, is the resultant. Maybe even going to call this the quickest way, right, to get from the first vector starting to the end of the second vector. The second method is called tail to tail, which means, if you notice that on both of these, they're the same starting stuff, is that A and B, what they can do is take B and now move it so the tails are touching each other. I still leave B and A facing the right direction that they started with. I'm not changing that. But now what you can do is you have to use a little copy and paste action. You need to say, oh, this is at a, say, 35-degree angle right here, right? 35, 40, I'm not sure. I don't have a protractor on this. But you're going to copy and paste it. That means make an exact copy, which means same magnitude, same angle, and you're going to paste it as a dotted line starting at the tip of A. So then, therefore, you end up with this dotted line. You do the same thing with A, copy and paste it starting at the tip of B. And what ends up happening is they eventually will form a box or a parallelogram. That point where the two new copied and pasted vectors come together is the point where the vectors would push this object. And then you connect it with the green straight across, and that is A plus B. That vector is the combinedness of that. I put on the bottom there, it says, note, to add two or more parallel vectors with the same exact direction, you just add their magnitudes. That's the cool thing. The length of the line just gets bigger by the other one. Hence, when you're trying to help push a car, if more than two people push on the car in the exact same direction, your forces kind of get added together towards that car. Also, you think about it is, if you're pushing a box on the ground, they always tell you to get low on the box, right? So you can push it straight across the floor versus pushing down on the box, because you're pushing then some of your force into the ground, causing more friction, and you're losing your ability to actually be as efficient. You want to get your direction of the force to be with the direction you want things to go. It's pretty cool. First examples that we have for today is I want you to find the resultant of these two vectors. We got two different sets on this page. It says find the resultant of each pair of vectors using either the triangle or the parallelogram method. State the magnitude of the resultant to the nearest centimeter. That's why I wanted to say, hey, bring some rulers. And it wants to know the direction relative to the horizontal, which means positive x-axis. How far up would you have to go from your starting points? Okay. This is going to get interesting because I don't have copies. This is just a picture. I'm going to do my best here. The first one I want to do is I'm going to use the tip to tail method, method 1, on the first group. Okay, so let's try this once. I made a copy. Is that cool or what, guys? So I made a copy. I'm not changing its size. And now what I'm going to do is I'm going to take the blue line, which I also made a copy of, and I'm going to add it to the tip there. Notice that these should have, right, lines, because those are the tips. When I want to add V plus W, I should be able to start here, right, and go straight across to the tip of the blue. I'll make it green because you're using green in the book. This might get a little wonky on us. Nope. Oh, not too bad, huh? Oh, technology's awesome. So there you go. So you now have just created the photo, or are you guys able to do that on your own? Okay? Making a copy paste, you measure it, do those types of things. So I'm going to pause it so we can make some measurements here. Okay, so when I would take my parts and put them together, I would be going 1.5 over and then 0.8 up. It forms a triangle. Eventually we're going to learn that you guys are going to have some law of sines, law of cosines. Once you've created some of these, you're going to have to use some of these properties. For today, they just want you to take your ruler and measure this guy right here. The book, because it's hard for me to get on here with the protractor and actually give you some accurate sizes, says that it should be 2.9 centimeters. And then it says, give me the relative direction to the horizontal. It's direction. So, what it's asking us to do is say, hey, there's my horizontal, yes? What is this angle? And again, if we actually took our protractor to our papers, now granted guys, you can make your own outlines up. Whatever you guys put into your paper are the ones that you guys will be using. So make yours, try to make something that's 1.5. Try to make something that's about 0.8 centimeters. And see if you guys can come up with numbers that are relatively close to this. They won't be perfect. They say at 61 degrees. You got 61 degrees to the horizontal, and it's 2.9 centimeters away. So for our next one, I'm going to use the other method, the parallelogram. So what I'm going to do is I am going to take these lines and I am going to make copies of them. And so here we go. Copy, paste. So I'm going to put one down here. I'm going to come up here, grab an A, copy, paste, and I'm going to place the tails together, yes? Now what I'm going to do is I'm going to place the B value, another B, at the end of A. And I'm going to put it's kind of like the tip to tail, but yet alternating their colors. So you guys should be able to do something like this with your own colors. And look at that. And so the vector will be that guy. Is that cool or what? Obviously, we're forming triangles. Am I allowed to use the Pythagorean theorem on this stuff? If it's a right triangle, the only way you can guarantee it's a right triangle is if you're given something about your angles being all of a sudden coming together at 90s, right? So don't assume, but you should be able to do that if only if it meets at rights. Your book says that it should be 3.3 centimeters and that it's 25 degrees. So when you guys measure yours, you should be able to piece things together. Okay, cool stuff. This one might be a little bit easier to do because you'll have to draw your own diagram. A pinball is struck by the flipper and is sent 310 degrees at a velocity of 7 inches per second. The ball then bounces off a bumper and heads 55 degrees at a velocity of 4 inches per second. Find the resulting direction and velocity of the pinball. So where did the pinball go? In which direction? After all the hits. Right? Here's the cool thing. 310 degrees, which way is it going? It's a little different than your normal quadrants. 310 from true north, right? Or true? Which means, if I was to draw a diagram here, that's 270, so somewhere over here, right? I'm going to get rid of these for a second. I'm going to try using a protractor. Okay. If I did this, how many degrees more than 180 is it? Because we're going to go all the way to 270, right? Actually, it's 270. 270 plus what is 310? It's another 40, right? So, according to that exact middle, I need to go about there. That's the direction it's going the first time. I'm wondering if I should move this. This is the first time trying to do this on a device, so bear with me. So, again, we need to have 4 inches per second. So, it doesn't matter, guys. This is the cool thing. Just because it's in the inches there does not mean you need to take a 20 by 20 piece of paper and actually make it work. Scale it. If it's easier to go in centimeters, then go in centimeters. So, if I go 4 centimeters in that direction, that means I will end up going to about there. So I am going there. I know that's not perfect, but that is 4 centimeters, or, oh, it's supposed to be 7. Darn it. 7. We got to go 7 instead. So we have to go 7. So I go all the way up to there. Okay, so that's 7 inches. Sorry, now we have to go 55, right? Now remember, when we go 55, we are going to do the tip to tail, right? So that means that's my new starting spot. And so when I'm going to go 55 from there, I'm going 55 from north, outward. And so where's 55 degrees? 55 would leave me with a reference angle to the x-axis of what? Because that might be easier for me. Because then I can use my x-axis. I have to go 55 in this direction. What would be the leftovers? Adds up to 90. 35? So 35 is all way out there. Got some extra coloring in here. This one's only 4. got to make sure I have on my colors. So it's out to there. So it's going to be something like that. So where is this pinball actually heading? What direction? It's from the origin to the end of that purple right there, right? It takes time. Obviously it's taking me more time because I'm trying to do this on a screen. There it is. That's going to be really close to what heading? What bearing? Not all at once. It's almost a full circle, right? So it should be bigger than 310, but it's going to be less than 360. So, figure it out. To me, it looks like it's about 14 degrees from 90. Which means, if it's 14 degrees from 90 in this direction, how many degrees would it go the other way? .346. Okay. And then, length. I have a length of 7.3. So it's 7.3 inches is what the line says for me. Yours might be slightly different. Yours could be more accurate than mine if you did everything on paper. So this is not really difficult work. It takes a little bit of thinking. But thinking's okay. Okay. The next up is the zero vector up top. When you add opposite vectors, it's denoted as 0. I could not find the thing with the line on it on the internet or on my thing, so you can put the vector notation above it. So that's a 0 vector, or darkened 0. It's also good to know that multiplying vectors by a scalar. If a vector v is multiplied by any real number scalar k, the scalar multiple of kv has the magnitude of absolute value of k times the magnitude of v. If you multiply a vector by a scalar, its magnitude is multiplied by that scalar. The direction is still determined by the sign of k. So if k is positive, it's the same direction. If k is negative, it's the opposite direction. And so we'll talk about how to do 4a there, but I would just use the tip to toe, or tail to tip method 3 times, right? But here's the thing, a minus c, that's not too bad. I could subtract those, which means, wait a minute, if it's minus c, is c still going to go in that direction? No, it means it flips it. Makes c go in the opposite direction. So you'll know then that you have to go make something like c opposite. And it's a really bad c representation, right? But you guys get in the picture. It's going the other way. Or if you like this better, go that way. Cut that off. Make it go the other way. It's opposite of c. And then it says 2b, which means it's still going to go in the same exact direction. It's just that I'm going to double its length, because it's going to be twice the magnitude. And then you can start to add them tip to tail, just like before, and then connect it from the beginning all the way to the end. Questions? This is where you're going to want to use a protractor, so I would pick one up if you don't have one. And I think this might be one of the last, nope, not the last questions. But relative velocity of a vessel is the resultant when the heading velocity and other forces are combined. So we got to figure out, where's Mitchell going? Mitchell swims due east at a speed of 3.5 feet per second across the opposite bank of a river. At the same time, the current of the river is carrying him due south, downward down the river, at a rate of 2 feet per second. Find Mitchell's speed and direction relative to the shore. Last year, you guys may have done things like this pretty close with the ship in the water or boat in the water problems and some other things. But it just comes down to creating your vectors. This one's not too bad because one of your directional vectors says directly what? East. The other one is south. Those are directionals. Those actually will cross at 90s. That's actually kind of interesting there. We could possibly use some Pythagorean identities here, or Pythagorean theorems. It's in feet. Guess what? I'm going to use my ruler, and I'm going to be in centimeters, or inches. We can go inches on this one probably. So, think about this, is that he's going to start right here, and he's going to go due east 3.5 feet. So, he's going due east 3.5. 3.5 feet. The river is taking him where? Which direction? Due south at 2 feet. Not all at once. 2 feet. Where is he going to eventually be? Does he actually make it straight across the river? If you wanted to catch him on the other side and give him a high five for swimming across this thing. Okay, so we got a river here. We'll use brown for sand. Are you going to meet him right there? No, you're going to meet him here, right? Because he is going to be carried to there. That's when he's getting out of the water. Now, granted, guys, he's not fighting the current at all, is he? He's just swimming straight across. And so here's the cool thing. This is 2 feet. Because these are at right angles, you could use your trig information, 3.5 squared plus 2 squared, add them together, square root, what is his actual speed on the river? Is he going faster than 3.5 or slower than 3.5? What are you thinking? Well, look at the line. Is it bigger or smaller than 3.5? It's bigger. He's going faster than 3.5. How is that possible? It's because the current is taking him downriver with some of it. So he's gaining some speed going down the river. What is 3.5 squared plus 2 squared and then take the square root? Someone's got to have a calculator about handy. No? We'll just let the video roll as we're waiting here, huh? So 16.25, so square root that. What do we get? 4.03? 4.03, but wait a minute. If we say this is a right triangle, can't I find theta? And if now we're talking here. Are we talking about what kind of navigation are we talking about? Do we want to use true? Because if I find theta, I don't know what theta is. We can use the inverse tangent, right? If I found tangent to say be 25 degrees, which I don't have right now. Does anybody actually have the actual answer there? I could look it up real quick here. They don't have the exact answer. It looks like it comes out to about 30 degrees actually. So let's go with 30. If say it's 30 degrees there. If I wanted to use true bearings, what's the bearing? What's the bearing if I have 30 degrees in there? It's not 60. Because true bearing starts at the north, right? The true bearing should start up at our north side right here, which means 90 plus the 30, which would actually be 120 degrees at 4.03 feet per second. Or could I do south 60 degrees east at 4.03 feet per second? Both of those work. I'm going to enter there. Homework's on page 488. Day 2 is 13 through 15, 27 through 29, and 35. Have a great day.